All right, in the first video, we talked about the differences between implicit and explicit forms. So now we're gonna implicitly differentiate implicit functions. So we have to have an implicit function to start with. And here are the guidelines to implicitly differentiate implicit functions. So what we're gonna do first is to differentiate both sides of the equation with respect to x, and we're going to try to collect all the terms involving dy over dx. And remember that dy over dx has to pop because we have to use the chain rule for the terms involving y functions. When we take the derivatives of those, dy over dx pops anyway. And we're going to sort of like collect all dy over dx in one side of the equation and the rest in the other side of the equation. And we're going to factor out dy over dx and solve for dy over dx. So this is a four-step guidelines for implicit differentiations. And we have two cool examples to explain the guidelines for you step by step. So let's start. All right, here's the first example of the video. So we're going to find dy over dx for this implicitly provided function to us. And it's obvious that this function is implicit because y is not provided us explicitly. So in the first step, we're going to take the derivative of the whole equation. Okay? In other words, we're going to take the ddx of both sides of the equation. And on the left-hand side, we have the sum or difference of each term. So why don't we divide and conquer? So we have to split the derivatives onto each piece here. And this is what we have. So now we're going to individually take these derivatives, okay? And x-related derivatives are just easy because we're going to use the rules for differentiation. Like for example, for this one, we're going to use the power rule for differentiation. This will take us to 2x, and this is a constant function. The derivative of that is going to be 0. And for all y-related terms, remember, we're going to use the chain rule. So here we go. This is one y-related term. So this is y quantity cubed. So by using the generalized power rule, 3 down, subtract 1 from the power, and multiply this by dy over dx, which is the derivative of the inner part. And same thing applies here. Let's apply the chain rule. 2 times y times dy over dx. And for this one, it's simply 5 times dy over dx. All right, bringing them all together, this is exactly what we have. And in the next step, we're going to try to collect all the dy over dx terms in one side of the equation. Here we go. All right, so what that means is I'm going to add 2x to both sides of the equation so that dy over dx are going to stay on the left-hand side of the equation. So in the left-hand side, that's where dy over dx terms are collected. I'm going to factor out dy over dx. So dy over dx factored out, either on the left or on the right, doesn't matter. So 3y squared plus 2y minus 5 equals 2x. That's going to be my third step. Here we go. That's the third step. dy over dx factored out. We have this quadratic term for y. And now in the fourth step, we're going to solve this equation for dy over dx by dividing both sides of the equation by this factor here. And in turn, we get 2x over 3y squared plus 2y minus 5. So we have the full description of dy over dx coming out of implicit differentiation. Well, first observation here is that you have the dy over dx just found. Now we can implicitly plot this function here, implicit function, and you can see that this is not a function of x because, you know, it just doesn't pass the vertical line test. But you can still talk about dy over dx, the slope of the tangent line, at certain points on the curve, right? So for example, if you look at 2 and 0, you can talk about the slope of the tangent line by using the form dy over dx. All you're going to do is to plug in 2 for x and 0 for y here, so that you're going to find dy over dx. So that's going to be the slope of the tangent line here. So the tangent line looks like this, so you will come up with that tangent line and its slope. And for other points, you can essentially apply the same thing. So you have 1 and -3. You have a horizontal tangent line here, right, at x equals 0. You can also find slope at 1, 1, undefined, because dy over dx becomes 2 over 0, which doesn't exist. That means you have a vertical tangent line at that point. And here is the tangent line at the point at 2 and 0. And here is the tangent line at the point 1 and -3. And here is the tangent line at this point here, -3 for y. So it's a horizontal tangent line. And finally, here is a tangent line, the pink line, at the point 1, 1. You have a vertical tangent. All right, the next example is about finding the slope of a graph implicitly. And in fact, this is the graph of lemniscate, and it's a figure 8 type graph. And what we're going to do is to find the slope of the tangent line at the point 3 and 1. And this time, let's do this all together. So I'm going to do dx of both sides of the equation first. That's the first step in the guidelines. And remember that whenever I see a y-related term, I'm going to use the chain rule or generalized power rule. And in fact, it's a power term on the left-hand side. So why don't we use the power rule for differentiation here. So 3 times 2 equals 6. 6 times x squared plus y squared to the power of 1, which is just x squared plus y squared, times the derivative of the inner part. Well, I have x squared and y squared in the inner part. For the derivative of x squared, we're just using the power rule for sure. But for the derivative of y squared, we're going to use the chain rule. So I'm going to just leave it as is, okay? And the next step, I'm going to take care of that. And for the derivative of the right-hand side, we have the product of x and y, and we can pull out 100 without a problem. So we're going to use the product rule. So this is, let me just write the full thing, d dx of x times y plus x times d dx of y. Okay? So now let's find those individual derivatives. So 6 times x squared plus y squared, 2x plus the derivative of y squared. Let's use the chain rule. So that's going to be 2 times y times the derivative of the inner part. Inner part is just y. So dy over dx is the derivative of that. So here we have 100 times d dx of x. Well, that's just the derivative of x. That's 1. So 1 times y equals y. Plus x times the derivative of y. That's, even if you use the chain rule, you're going to have dy over dx. Okay? So now let's expand everything out. So you have 12 x squared plus y squared times x plus 12y x squared plus y squared dy over dx, and 100y 100x dy over dx. And as part of the second step, we're going to collect all the dy over dx terms in one side of the equation. So that means I'm going to subtract this term from both sides, and also I'm going to subtract this term from both sides. All right, let's see what we have. I'm going to also factor out dy over dx, so I'm doing step 2 and 3 in the meantime. So we have 12y x squared plus y squared minus 100x dy over dx equals 100y minus 12x x squared plus y squared. And as the final step, we're going to divide both sides by the coefficient of dy over dx. Here we go. So 100y 12x x squared plus y squared divided by 12y x squared plus y squared minus 100x. All right, this dy over dx hides all the information about slopes, but in particular, we're interested in the slope of the tangent line at the point 3 and 1. 3 and 1 means that x equals 3 and y equals 1. So we're going to go ahead and evaluate dy over dx at 3 and 1. Here we go. So we substitute 3 for x and 1 for y, and we get that the slope of the tangent line is 13 over 9, and here is the blue line. Here is the tangent line that comes with the positive slope, 13 over 9. As I said, this is an 8 figure, and it's the lemniscate, and here is the tangent line. Right, this ends the discussion of the implicit differentiation to find the derivatives of implicit functions. In the next video, I'm going to talk about logarithmic differentiation. Please move on to my next video to see what I'm going to say about it. All right, bye.